Hello everyone. In the lecture today, we will start the introduction about the topic in route surveying, where we will learn the measurement of the road geometry in transporting system. Basically, the route surveying can be categorized into three types, including the calculation of the curves, the estimation of the cross-section area, and the calculation of the volumes for the earthwork. We will especially focus on the first one, the curve calculation for horizontal routes, super elevation, and vertical routes. The route survey is usually applied for transporting system, and we know that in transporting system there are road networks, and vehicles and trucks can travel in the networks to transport both goods and people. The route surveying can be applied to design the geometry of the highway, railway, rapid transit guideway, and canals. It can also be applied for the design of the pipelines and transmission lines. In this class, we will focus on the design about the highway geometry with the route survey. In highway alignment, we first need to measure the geometry of the horizontal and vertical curves, and we are especially interested in identifying the smooth connections between straight sections. Also, we have to identify an appropriate methods of acquiring terrain data for the region we want to do the construction work. And with this information, we need to estimate the volume of the earthwork and find out an efficient distribution process for the earthwork. One major objective of route surveying is estimating horizontal curves to connect two straight segments smoothly. For example, if we consider two segments, one is from A to B, the other one is from C to D. The horizontal curve will connect the point B to C and the two segments AB and CD were tangent to the horizontal curve, while the design for the vertical alignment is a little bit different. The purpose of the vertical alignment is trying to find out a smooth connection for two segments, say that EF to FG, with different degrees, S1 and S2. In the vertical alignment, we will introduce the arcs of the parabolas to connect these two segments smoothly. First, let's go through the circular connection of the straight segments for horizontal curves. The figure here shows two horizontal curves for the connection of three segments, which would be the horizontal curve 1 and horizontal curve 2. In this figure, you can see three different types of the points, PC, V, and PT. Here, PC is the point of curve, which is the start point of the horizontal curve, and it will connect the curve with the preceding line. And the PT is the point of tangent, which is the end point of the horizontal curve, and it will connect the curve to the following segment. Also, V here represents the vertex of, is actually the intersection of the preceding and following segments. The route survey is trying to identify the location of the set of stations along the route. We usually will start with the given station, say that 1 plus 0, 0, 0. It means that the distance measured at this location is 1,000 meters. And then we are also provided with a fixed interval. In this case, it's set as 20 meters. And along the route, we will set up stations at every 20 meters. So we have station 1, station 2, and we also set up a major station at every 100 meters. So the distance at this station is 1100 meters. So we need to identify the location, including the horizontal and vertical location of each station along the route. For the estimation of the horizontal curve, we first need to identify an appropriate measurement for the circular connection. Usually, the curvature of the circular connection can be measured based on the degree of the curve, and there are two types of the definition for the degree of the curve. The first one is the arc definition, and the definition is shown in the figure here. In this figure, we have LA as the length of the curve, and R is set as the radius of the curve. And then dA is defined as the degree of curve based on the arc definition. With that, we can define dA by the following equation as dA over LA equal to 360 degrees divided by 2 pi r. In this equation, you can see that 2 pi r is the perimeter of the entire circle. Usually in the metric system, dA is defined as the angle with the arc length of 100 meters. So that is dA divided by 100 equal to 360 degrees divided by 2 pi r. And in this figure, it's shown as the angle with the length of 100 meters. The degree of the curve can also be defined based on the chord length. For example, if we consider a curve from point A to B as shown in this figure, then the chord is defined as the straight line to connect point A and B. In that sense, the degree of the curve with the chord definition is set as the angle with respect to the specific chord length. In the metric system, the standard chord length is set as 100 meters. And from this figure, you can see that if we connecting the center of the circle with the midpoint of the chord from A to B, then we will have the right triangle, and the value about the angle here is a half DC. With that, we can find sine half DC equals to 50 divided by the radius of the circle. And with this equation, we can find out the value of the degree of the curve based on the chord definition. In the estimation of the horizontal curve, we also need to apply some geometrical facts. In this figure, if we assume that the angle of the arc from A to B is delta, then we can get that the angle of DAB is half delta. Here D is the vertex of the two straight segments E to A and F to B. In addition, for any other points in the circle which is below the chord AB, we will have the angle like ACB equal to the angle of AC prime B and so on. They are all half delta. These two information is very important for us to estimate the horizontal curve. So in the summary about the geometric effects, we will have the first one, which is described as the angle of ACB is the same to the angle of AC prime B. For the second one, we will have the angle of DAB equal to half delta. Similarly, we will have the angle of dBA is also half delta. In addition, for the third one, we will have the distance of A to D is the same to the distance of B to D. And all those information will be applied in the future pages for the estimation of the horizontal curve. Now let's see how we can conduct the calculation for the horizontal curve. Assuming that we can measure the intersection angle for the curve A to B, and the angle is I as shown in this figure. We are also given the radius of the curve R. So that is we are given I and R. And we want to find out the length of the set of segments, including the segment of AV, which is the segment here, from point A to the vertex. DV, which is the segment from the middle point of the curve to the vertex. And DF, which is the distance from the midpoint of the curve to the midpoint of the chord. And AB, that is the length of the chord. So first, let's go to see the calculation about the segment A to V. For A to V, we need to call the triangle OAV. As the line A to V is tangent to the curve, we can see that the line OA is actually perpendicular to the line A to V. And also we know that the angle of AOV is just half of the intersection angle, so that is half I. Then we can derive the length of AV as AV equal to R times tangent half I. This is actually the feature of the right triangle. In the second, we can estimate the length of the segment D to V. In this figure, we can see that dV actually equal to the length of OV minus the length of OD. Here, obviously, we can see that OD is just the radius of the curve, so that is R. And for the length of OV, we can actually consider the right triangle of OAV, and we know the angle for here is half I, and the radius R. With that, we can find OV equals to R divided by cosine half I minus R. And that's the way for us to find out the value of dV. Next, we can calculate length of AB. For this calculation, we need to consider the triangle OAF, and we know that in this figure, OF is perpendicular to the chord. In that sense, the triangle OAF is a right triangle. Also, we know the angle AOF is half I, and the length of OA is just the radius of the curve. This indicates that the length of AF is r times cosine half I. As we know that f is actually the midpoint of the chord. In that sense, we can find out the length of AB as 2AF, that is 2 times R times cosine half I. With this information, we can then estimate the length of DF. For this calculation, we need to consider the triangle DAF. As we know that DF is perpendicular to the line AB, and also as the D is the midpoint of the curve A to B, we can get the angle DAF as half of half I, that is a quarter I. With this information, we know that the triangle DAF is in the right triangle, and we know the angle here is a quarter I. Then we can estimate the length of DF as AF times tangent a quarter I. By using the value of AF we derived in the third part, we can get the length of DF as R times cosine half I times tangent a quarter I. So with this, we can find out the length of AV, DV, DF, and AB. In the estimation of the horizontal curve, we also need to calculate the length of the curve. There are actually several methods for the calculation. The first method relies on the radius of the curve R and the intersection angle I of that curve, which means we are given R and I. With that, we can find out the length of the curve, say that LAD as I over 360 degree times 2 pi r. Here, 2 pi r is the length of the circumference of the circle. So that's the first method. In the second method, we can actually use the degree of curvature, especially degree of the curvature with the arc definition, for the estimation of the curve length. In this method, we are given I and also the degree of the curvature with the arc definition. Then the length of the curve LAD can be calculated as 100 times I over dA, as dA is actually defined based on the standard length of 100 meters. In the third method, we can actually use the degree of curvature with the chord definition for the estimation of the curve length. So we are given I and DC. Then we can find out the value of the length for the curve A to D as 100 times I over DC. Well, in this case, you only get the summation about all the chord with respect to the intersection angle. And this is just an approximation of the true curve length. At most of the case, the approximation is less than the true length. So those are the three fundamental methods for us to estimate the length of the curve. And we will apply this method in the future for the horizontal curve estimation. Finally, let's check one example to see how we can use the proposed curve formulas for the estimation of the variables applied for the design of the horizontal curves. In this example, we are assuming that the intersection angle of one curve from point A to B is given as I equal to 60 degrees 30 minutes. And the length of the segment E, which is the line from D to E, is given as 125.45 feet. We want to find out the radius of the curve R, the degree of the curvature based on the arc definition, and the chord length. First, let's see how we can calculate the radius of the curve. In the solution, we can call the curve formulas that we defined in the previous pages. For the value of E, which is the segment of DE, is defined as R over cosine half I minus R. So this one gives us the value of R equal to E divided by cosine half I minus 1. We know the value of E is 125.450 and the value of I is 60 degrees 30 minutes. So we have cosine 60 degrees 30 minutes over 2 minus 1. Solving this equation, we can find out the value of the radius as 759.862 feet. So that's the calculation about the radius of the curve. And then we can check the definition of the degree of the curvature for the arc definition. So we have dA over 100 equal to 360 degree divided by 2 pi r. With that, we have dA equal to 360 degree times 100 divided by 2 pi, and r is given as 759.862 feet. So we have the value of dA as 7.20 degree, which is 7 degree 12 minutes. And finally, we can go to check the value of the chord length. From the figure, we can see that C will equal to 2 times AF. And also we can get AF is R times sine half I. So that is 2 times 759.862 times sine I is 60 degrees 30 minutes divided by 2. With that, we can find out the value of the chord length as 801.870 feet. So this example tells us how to use the curve formula to find out all the necessary information for the design of the horizontal curve. So that's all about lecture today. Thank you very much for your attention. Basically, in this lecture, we made a brief introduction about the basic concepts in the route surveying. We also introduced the definition for the curvature and also some curve formulas for the design of the horizontal curves. In the next lecture, we will focus on the introduction about the detailed procedures to design the horizontal curves.